Okay, if there are no questions, then let me start the proceedings. So I was telling you how to handle the interrupts, which will lead to handling the system calls, and that will lead to how Fox system call can create a process. That's what is this lecture series all about. So how Fox system can create a process, we'll see in the next lecture. Uh, if you guys are not taking it seriously, you better take it because it's not that easy. I don't believe that nobody has any question to ask. So if you have gone through this, you must be having some questions. So I'm again giving you chance. If you have any question, you can ask. Abhigyan,
No, sir.
so you understood how control is shifted to
So the that question you asked in the last class,
yes.
so that answer I didn't got, but I thought
So
you had.
you people are not asking that. That's the thing. Yes, anybody else? Anchal Tiwari, you got the answer, the question I asked in the last one?
So I tried to find so whatever I got is that whenever an interrupt occurs, then the IRQ number has to be. I mean that I don't remember the exact name. That number is seen, and then int instruction is executed to transfer the control to the kernel code. So that is what I understood, but I'm not sure if that is the answer.
Okay.
Yes, sir.
Okay, let me repeat the things. So we started with the instruction set architecture of x86, and then we reached to this slide. We discussed about the proc data structure, which I told you that corresponds to your process control block. I've shown you the code of x86 also in line number 2353. And make it as a habit of seeing the code of x86 because slowly and gradually you will require that. So at line 2353, this proc structure is defined in code of x86. And here we focused on these three underline and red color item. One is pointed to the bottom of kernel stack. Other was pointed to the trap frame structure. And the third was pointed to the context structure. Then we discussed that why these pointers are needed, and we discussed that these trap frame and context structures are different. On the next lecture, you will be able to differentiate between trap frame and context structure when we'll see the code of fork in detail. And why we require specific pointers for trap frame and context structure. You already have a pointer to the kernel stack, bottom of the kernel stack, and you can move to these structures easily because that is in the on the stack only. It is just for easiness so that you can swiftly locate these structures whenever the need is there. Then we discuss about the most important structure, data structure, that is P table. And P table was nothing but you can see the mouse pointer, the array of proc structures. And then I told you that this P table has to be protected by a lock for guaranteeing the mutual exclusion, that at a time only one process should be accessing this uh, P table. So P table you can consider is the array of the proc structure. Then what Anchal was telling, every interrupt has been assigned a IRQ number, a unique IRQ number. And whenever an interrupt occur, that IRQ number is used to index into a table, that is interrupt descriptor table, which stores the information that what to do with every interrupt number. And this is set up during initialization, and at line number 3317 you will find that how this interrupt descriptor table, depending upon the architecture and the nature of interrupt a certain architecture can experience, this interrupt descriptor table is initialized, is set up during the initialization. Now, what is happening in simple OS like x86? All the IDT entries, they may be for the different interrupt numbers, but they point to a generic function to handle all kind of the trap handling or interrupt handling starts from a generic function, one generic function known as all trap, and this all trap is defined in line number 3254. Now, to make the thing simply, because this OS is simple, for each interrupt, kernel will start executing at this common function. So whatever interrupt it is, it may be a software interrupt, it may be an exception, it may be interrupt from different devices, but all interrupt handling will start from this common function known as all trap function. Now, then I ask you this question, and I'll spend some time on this just to make you understand that why some spatial handling is needed here. So let me share my whiteboard first, and then we'll be able to see. Fine. Now the question here is, there is a CPU in your processing unit. Suppose a process P1 is executing. And for say simplicity, we can assume that we have a single core uniprocessor, because I just wanted to stress one point. So when P1 is executing on the single core uniprocessor CPU, at this time OS is not executing. It cannot execute because on one processor at a time only one process can execute. So at this time OS process is not executing. Now when P1 is running, P1 has already started or already utilizing the GPRs, general purpose register, the EIP, the program counter register. So as I told you that when a process executes, it uses the registers and all other things of CPU. Now what's the problem here? Suppose a interrupt comes. Actually, when an instruction is executing, until unless the instruction cycle is complete, interrupt handling cannot be performed. It may so happen that during this time, many different interrupts may arrive during this instruction cycle, but you will start handling the interrupt only after the completion of instruction cycle. Now to handle this in all the architectures, there is a hardware known as interrupt priority encoder. So there may be 2 or 3 interrupts pending because CPU was already executing an instruction cycle, so there may be 2 or 3 interrupts pending. So whom to service first can be decided by this interrupt priority encoder. So suppose you have a keyboard interrupt. So in any case, to handle the keyboard interrupt, you require a piece of code which is known as interrupt handler. So depending upon the IRQ number, the interrupt handler should run. And all these interrupt handler pointers, where these interrupt handler are in memory or in operating system, the pointers are stored in IDT, interrupt descriptor table. So this IRQ number would be used to know about which code to run. To make the thing simple in x86, handling of all interrupt start with a generic code, and that generic code is known as all traps that I've already explained. Now the question here is that how the control can be shifted from code of P1 to the code of all trap. That's the question. Because in code of P1, it's a user program. You haven't written a function call or a system call. And this interrupt is coming from outside in asynchronous manner, that it can come at any time. And P1 might be at any point of execution. So the question here is how we can shift the control from P1 to this all trap function. Because to call the all trap, who will, if all trap is a function, somebody must be there to call this all trap. This cannot come and start executing by magic. No, this cannot happen. So somebody must be there to switch the control from P1 to the all trap. Now the question here is, who is that someone? Who will do this? That's the question. Someone is needed. Someone is needed to call this all trap function. Now anybody can tell? Anybody? Yes, Abhishek Vaishnav, if you can tell something. So those who are on my screen, like Divyansh Bansal, Stuti Jain, Megha Gupta,
Hello, sir.
yes,
Am I audible?
yes, you are audible.
Yes, sir.
You want to say something in this?
No, sir.
What I'm teaching right now?
No, sir.
What's the discussion all about? What is going on right now?
Sir, interrupt, sir. Actually, I missed the last class. I haven't watched the recording.
Okay. Abhigyan, you want to say something?
Sir, I think, sir, there has to be some like trap handler in between of this also. In XV6 also, which calls that all traps function. Uh,
Okay. Anybody else want to say something?
So maybe there is signal from hardware to the operating system.
Can you elaborate a bit, Divyansh?
So I think whatever I'm getting is that since it's not possible for the software to get the interrupt, so maybe there's some hardware that detects some interrupt, then it sends a signal to operating system to generate all trap.
Now, the question here is, Divyansh, that if we like what Abhigyan was telling, that there's another trap handler kind of thing. So I mean that trap handler has to run, no? And to handle the trap, it will call the all trap function. The problem here is, then who will do these things? As soon as you run another program, that is another process, no? P2. It may be a trap handler, it may be anything. And when P2 runs, and we have assumed single core uni processor, just to make the thing simple, this discussion is without loss of generality true for multi-core processor also. So when P2 comes, the whatever P1 was doing on general purpose register, program counter, and other CPU related hardware will be overwritten. That's the question. So you are right that software cannot do this thing.
Sir, one more thing we can do. I don't know if it is true or not. So let's say if there are some X number of hardware needed to run a program, so we can make a operating system that we use only half of that and save half of that for interrupt handling, something like that for the backup.
It's not like that.
Okay.
So let me explain things. Actually, we require help from CPU only, because CPU was interrupted. It's not like P1 was interrupted. Ultimately, P1 is interrupted because P1 was executing on CPU. But CPU was interrupted. CPU got a signal that whatever you are doing, you have to stop that, and whatever signal is there, handle this. So there is a special purpose CPU instruction that is not part of the hardware. That is not part of your operating system. This is CPU instruction. It's not part of code of operating system. It's not part of code of user program. This is a CPU instruction known as int. So it's just like a suo moto kind of thing from CPU. And that's what is mentioned here in this slide. On interrupt program fault system call trap in XV6, CPU stops what it is doing and executes the int10 instruction. Int instruction, where n is nothing but the argument of this int instruction. It's a hardware instruction. Fine. Where n is nothing but the interrupt number. CPU execute int instruction, its own instruction, and interrupt number, whatever interrupt number is there, is passed as an argument to this int instruction. Same thing happens in system calls. When user program calls a system call, later on we'll see this int10 is going to be invoked. And that's what I've written here. Someone, either an external hardware device or the user, must invoke the int10 instruction to begin the processing of trap event. So we need someone to do this thing. User cannot do. Fine. User cannot do because user haven't written anything in its user code. Either user can do a system call, and system call ultimately there is a process of calling int10 instruction, or some hardware device has to do this thing. Let us see further. So before going there, first of all, let's see what this trap instruction is going to do, or int10 instruction is going to do. CPU moves to kernel mode. If it was in user mode previously, just a minute. I have to take this call. Sorry. So what is going to happen? CPU moves to kernel mode if it was in user mode previously. If it is in kernel mode already, then no change. The stack pointer, ESP, top of the stack pointer, moves from old stack, user or kernel, to the kernel stack of the process. If it is already in kernel stack, no change. Otherwise, it will be moving from user stack to the kernel stack. As part of the execution of int10 instruction, CPU also saves some registers on the kernel stack. Pointers to old code segment, old stack segment, old program counter, etc., which will eventually form a part of the trap frame. So as we'll see the trap frame, you'll be able to know. So most important things which may be overwritten if all trap function runs are saved by this int and instruction on the kernel stack. And now piece. So whenever there is a interrupt, CPU's int n instruction, where n is a argument of that interrupt number, is invoked, which does all those things, moving the stack pointer from user to kernel stack, moving the old code segment pointers to the old code segment, old stack segment, old program counter, etc. are going to be saved, which eventually form a part of the trap room. CPU fetches the IDT entry corresponding to the interrupt number. This is all part of that int instruction, which has a pointer to the kernel trap handling code. And control is now transferred to the kernel. CPU starts executing the kernel code, which is all trap here, that is responsible for handling traps. All these things in this slide and the previous slide is done by int n instruction, where n is the argument of int instruction, which is nothing but the IRQ number. So most important things of the currently running process are saved by this instruction, and then gradually control is shifted to the kernel. And then we start executing the all trap function. All of this is done by CPU hardware as part of the int n instruction, not by any software. And this logic is built in CPU processor hardware. So this was the important thing, how shifting of control from a user program to kernel code happens. And for that purpose, a special hardware instruction is there, which is a CPU instruction. Some important things you need to be very careful about. There would be change in instruction pointer, means there would be change in program counter from user code to the kernel code of interrupt handler. There would be change in stack pointer from old user stack to the kernel stack. And these all things must happen as part of hardware CPU instruction. It cannot be done by kernel software because the kernel can start executing only on kernel stack. So first of all, somebody has to move the control from user stack to kernel stack. Who will bring something from user stack to kernel stack? But this is a function call which is trying to fetch a routine of a kernel. So you have to be, your stack pointer should be shifted from user stack to kernel stack. You cannot directly execute a kernel code if you are still in user stack. Somebody has to change your program counter from user to the kernel code. It is imperative and very much required that some part of trap handling should be implemented as part of the hardware logic of the int instruction. So it's a hardware logic which is doing all these things. No OS code or something can do that thing. Because you are still in user stack, how can you handle a OS code? How can you call a OS code or kernel code? And I'm again stressing this that someone must switch control to kernel before kernel can actually start running. And that someone is hardware here, CPU here. Now any doubts? Brijendra?
No, sir, it is okay.
Abhigyan?
So in that uh, when we are running one process only, and you said that if we in the software we run another trap handler, then it all the counters will be overwritten.
How can you run a trap handler? Just tell me one thing.
Uh, man- I mean, like in the software we cannot do that only. But in this slide, sir, what are these? What counters are these changing, sir? This change in IEP and ESP. What are these changes?
This is program counter. You are in user code. So you need to change the program counter because next instruction which is going to be executed is from kernel code. Are you getting my point?
Yes.
What is program counter? Program counter register holds the address of next instruction to be executed. So you need to change program counter and
Yes.
give the address of kernel code over there. Means
Okay.
the address of alt-rap function to make it simple. But if you just overwrite with the address of alt-rap function, how can you return back to the P1 process from where it was interrupted? So you need to save this program counter and then jump to the kernel code. Getting the point?
Yes.
You need to return back to old user stack also. That's why you need to save the old user stack pointer also. Got the point?
Yes, sir.
Okay. So let's move ahead. Now, the kernel code pointed at by the IDT entry pushes the interrupt number onto the stack. First of all, what it will do, whatever the IRQ number is there, is going to be pushed on the stack. And now you start saving various registers. Now this all work is getting done by your alt-rap function. Interrupt instruction of CPU has done its work. This work is getting done by your alt-rap function. Pushes the interrupt number onto the stack. Complete saving various CPU register. Some of the registers are saved by the intent instruction of CPU. Now alt-rap function is saving register. Actually, it is building trap frame. So DS, ES, FS pointers to all these segments, data segment, extra segment, frame segment. Kernel stack now contains a complete trap frame. And this is given in line number 0602. Let's see the code. You can see here, this is your trap frame structure. Registers as pushed by push all. Rest of the trap frame. So everything is there in the trap frame. Got the point? Kernel stack now contains a complete trap frame. Fine. So alt trap, first of all, builds the trap frame. And as now clear to you that trap frame is built collaboratively by CPU hardware and the kernel. some part of the trap frame, EIP, etc. are pushed on stack even before the kernel is started to run. And who has done that? That has been done by the intent instruction. So अभी kernel चलना भी नहीं शुरू हुआ है, but some part of the trap frame are already pushed on the stack. And that is done by int instruction of CPU. The rest of the fields are pushed by all trap function in the kernel. And I have shown you the trap frame structure on sheet 6. Bottom parts of trap frame are pushed by CPU, top parts by kernel. You can see here. This EIP, CS, all these are pushed by CPU, and these part are pushed by the all trap function. And finally, you will be having a trap frame on the stack, because you need to return back also. You need to return back also to the already running process, and you have to return back to the same point from where that running process was interrupted. This trap frame serves two purposes: saves the execution environment or context which was existing just before the trap, so that process can resume where it left off. Provides information to the kernel to handle the trap. Then the main C function to handle traps defined at line 330 is invoked at line 3272. After doing all these things, to handle the trap, after all trap, the main C function would be invoked, and this main trap function is defined at line 3350. Let's see 3350. You can see here, this is trap function, and the pointer to this trap function, the argument to the trap function is the trap frame, which you have just built using all trap function. Now here, depending upon the trap number element of trap frame, you will be handling different interrupts. So in short, what's the story? All interrupts would start getting handled by a common function, that is all trap function. All trap function will build a trap frame. Some part of the trap frame is already built by your CPU instruction. Fine. Some part of the trap frame is already built by CPU instruction int. Rest trap frame will be built by all trap function. And after doing this thing, then you call the main C function to handle trap. And now depending upon the IRQ number, which is part of your trap frame, depending upon the IRQ number, you can see here in the code, you are checking TF trap frame trap number, TF trap number. Depending upon the IRQ number, you are handling different interrupts. One more thing. Can anybody explain me this line? But before this function is called, the stack pointer is pushed onto the stack as an argument to this trap handling function. आप लोग को बताया था मैंने कि whenever we call a function, when a function is called, the argument to that function would be stored on the stack. Remember that slide? If you can go behind, I've explained this. All these caller save register, callee save register are there, and then if there are arguments to that function that are, I've given one example of A1, A2, A3, A4, if you remember. So from right to left, you store the arguments on the stack because you never know whether those registers where these arguments are stored are going to be used by callee function or not. So before doing that, before calling the main trap function, you need to push the argument on the stack, and this argument on the stack is what? What is the argument to the trap function? Is a pointer to the trap frame. And pointer to the trap frame means address of the trap frame. And trap frame abhi hai kahan? On top of the stack. So just push the ESP over stack, the content of stack pointer register. So this work, pushing argument on stack, is automatically done. So you are not required to clear any register or do all those kind of things, which is also a pointer to trap frame, since the trap frame is there at the top of the stack. So पूरी कहानी फिर से, fine. Let me complete this, and I'll repeat everything. Main logic to handle all traps is in the C function trap starting at line 3350. Fine, this trap function. This function takes the trap frame as an argument, looks at the IRQ number of the interrupt in trap frame and executes the corresponding action. As you can see here, looks at the trap number of the trap from the trap frame and do the processing what is needed. If it is a system call, as you can see, if trap number is T syscall, and this was covered in the lab, then we will be doing another thing to handle the system call. If it is a trap from the disk device driver is called. From IDE device. If it is a trap from the timer, then we need to check the timer interrupt, and so on and so forth. So हो क्या रहा है? All trap सब कुछ सेव कर रहा है, फिर trap function कॉल हो रहा है, trap function all trap ने क्या सेव किया? trap frame बनाया. अब ये trap function क्या कर रहा है? उसका argument trap frame का pointer है, trap frame में अंदर जाके trap number निकाल रहा है, और ये main trap function अब handle कर रहा है different interrupts को. After handling the trap suitably, that particular interrupt, trap function returns to line 3272 from where it was invoked. Let's see line 3272. Here, you have called the trap. Before calling trap, you can see you are pushing ESP to the stack. Fine. And then calling trap. After the call, you return here. And you can see, हम top of the stack को delete कर रहे हैं क्योंकि ESP का काम अब खत्म हो गया, आप वापस आ गए. So what is happening? All trap will call the trap function will see the trap number, handle the interrupt, and return back to line number 3272 from where it is called. Afterwards what will happen? अब कोई बताएगा क्या करना है? सॉरी, अभिज्ञान आप क्या करेंगे? प्रोसेस चल रही थी,
Yes.
ट्रैप आया, ट्रैप हैंडल हो गया, हम वापस आ गए।
तो सर तो फिर वापस प्रोसेस को चालू
अब प्रोसेस को कैसे चलाएंगे?
कर
तो जो प्रोग्राम काउंटर और वो सब है उसको रिस्टोर करना पड़ेगा ना उस प्रोसेस को चलाने के लिए।
यस सर।
स्टैक पॉइंटर और सबको।
हाँ।
तो जो पुश किया था हमने स्टैक में उसको
वो सब
अब अपन पॉप
पॉप
करेंगे,
करते
सो दैट पुराना वाला कॉन्टेक्स्ट फिर से अपने अपने रजिस्टर में पहुंच जाए सीपीयू पे। Simply speaking, what is happening, a process was running before trap interrupt handler can run. तुमने प्रोसेस का जितना भी स्नैपशॉट था उसको स्टैक में पुश कर दिया, तुम सिक्योर हो गए कि नहीं यार मेरी प्रोसेस का सब कुछ माल मसाला अब स्टैक पे आ गया। इंटरप्ट हैंडलर आया, उसने एग्जीक्यूट किया, वहां पे उसका काम खत्म हो गया इंटरप्ट हैंडलर का। अब इंटरप्ट हैंडलर रिटर्न हुआ, कोई फंक्शन कॉल होगा तो रिटर्न होगा, रिटर्न होने की जगह दिखाए तुमको, कॉल ट्रैप के पास रिटर्न होगा। अब रिटर्न होने के बाद क्या करना है अपन को, जो कुछ भी हमने डाला था स्टैक में उस सबको एक एक करके वापस लाना है। किधर लाना है? अपने सीपीयू रजिस्टर से। प्रोग्राम काउंटर लाना है, स्टैक पॉइंटर लाना है, सब रजिस्टर फिल करने हैं, सो दैट द process which was interrupted can run from where it was interrupted. Just see here, after trap returns, it executes the logic at trap ret. There is a trap ret function which is defined in line 3277. See here, trap ret, pop, सब कुछ पॉप कर दिया। तो जो कुछ भी ऑल ट्रैप ने नाटक किया था, पुश किया था, वो ट्रैप रेट ने पॉप कर दिया। एक और है यहां पे आखिरी में 3284 पे, आई रेट। आई रेट क्या कर रहा है? एनी आइडियाज? After trap returns, it executes a logic at trap rate. Registers that were pushed on stack are popped by operating system. So OS ने जो रजिस्टर पुश किए थे वो OS ने पॉप कर लिए। देन आपको फिर से एक हार्डवेयर इंस्ट्रक्शन iret चलाना है। जो सीपीयू ने पुश किए थे रजिस्टर्स int इंस्ट्रक्शन यूज करके, those are going to be popped by iret instruction. This is inverse of the int instruction, pops the registers that were pushed by the int instruction. And now the context of process prior to the interrupt is restored and user space process can resume execution. The trap handling is complete. Any doubts?
सर
Yeah, Brijendra.
सर जैसे ये जब इंट कॉल हो रहा है, जैसे मान लीजिए कीबोर्ड से आया इंटरप्ट या नेटवर्क इंटरफेस कार्ड से आया, तो यहाँ पे सर IIRQ नंबर तो डिफरेंट होगा, तो यहाँ पे वो एज एन इंट के लिए आर्गुमेंट हो जाएगा। तो सर ये उसको नंबर पता कैसे चल पा रहा है? क्योंकि जब इंट कॉल होगा, इंट मतलब हार्डवेयर चलाएगा, तो उसे n चाहिए, तो n उसको मिल कैसे रहा है?
वो सिग्नल आता है, पिन नंबर होता है।
तो मतलब हार्डवेयर
हाँ, हार्डवेयर
सीपीयू पे पिन बने होते हैं, जिस
सीपीयू
पिन
का
के
पिन नंबर, हाँ, जो पिन अप होती है
हाँ,
वो लाइन
वही
अप
नंबर
हो
है।
जाती, वो लाइन, ये हार्डवेयर में ही इम्प्लीमेंटेड है इंस्ट्रक्शन, ठीक है। तो
यस
तुमने पता नहीं ध्यान है कि नहीं, माइक्रो प्रोसेसर का जब देखो ना तो पिन नंबर, पिन डायग्राम
यस
आता
सर,
है,
यार पिन रहता है उसमें,
तो वो
तो मतलब वो पिन से ही
IR7
लेता है वो।
पिन से ही लेता है, वो हार्डवेयर ही है। तो पिन नंबर का है ये, वही पिन ले लेता है। एक्चुअली वो नंबर नहीं है, वो पिन का जो अप हो गया सिग्नल उसी को ले लेता है,
हाँ,
उससे पता चल जाता है उसको।
हाँ,
इसको ऐसे समझो ना, it's not memory mapped IO, it's IO mapped IO.
यस सर,
You got my point or not? So
यस यस सर,
memory mapped IO तब होता है जब मेमोरी में IO डिवाइस का एड्रेस होता है. It's a kind of IO mapped IO where, like, in our system, monitor is also having a address. But monitor address is IO mapped IO because it is connected to some COM port behind, and that COM port pin number is giving you the address. Are you getting the point?
यस सर, यस सर,
In this way we can get the things.
because in software interrupt we already provide the number, that is in our case 64.
That is 64. अब 64 उसको आ गया तो वहाँ डिफॉल्ट केस चल जाएगा इंटेंट के,
यस सर,
ठीक है, कि अब
मतलब
उसको
वहाँ
कुछ
पे यूजर प्रोग्रामर दे ही रहा है, क्योंकि जब वो लाइब्रेरी इंप्लीमेंट कर रहा है सिस्टम कॉल के लिए, तो वहाँ नंबर देता है बाय डिफॉल्ट।
वो हम अभी तुरंत ही बताने जा रहे हैं,
यस
यूसेस वाला जो है, ठीक है।
यस।
एनी अदर क्वेश्चन? यस, अभिज्ञान?
No, sir.
Now you got the point?
Yes, sir.
Any other question from anybody? Let me call some names. Chitish Verma, are you there?
Yes, sir.
Any doubts?
Sir, actually, my network connection is dropping every time, so I'll have to watch the recording again.
Okay.
Yes, sir.
So when will you ask your doubts then? In the next
Sir,
class?
Sir, maybe in the next class, maybe in lab.
Maybe in lab. Okay.
Yes, sir.
Okay. Rajiv Ranjan?
Yes, sir.
Any doubts?
Yes, sir.
Any doubts?
No, sir.
Got it? Everything?
Sir, I have missed 1 or 2 classes, sir. So I am just brushing of previous class.
You're not audible properly. Can you come again?
Sir, I have missed some of the classes, so I am revising
Miss
the
some of the
previous one.
classes. No problem. No problem. Srishti Singh? Srishti Singh? Viraj? Tanmay Dhawan?
Sir?
Any doubts?
No, sir.
What is IDET instruction? Tanmay?
Sir, can you repeat?
IRET instruction, I've just explained.
IREC instruction.
IRET, just explained.
So, okay, IREC instruction. So, it reverses the operation basically.
Which
Like,
operation?
how to explain? Say there's a call or a int, for example, so it will basically just reverse it.
What int does?
What does int do?
Hmm.
So,
Anyway, Shivan Shukla.
Yes, sir.
Any doubts?
No, sir.
Clear?
Yes, sir.
Okay. Okay, so let's move ahead. And now we are good to go with the system call handling. And system call handling, a little bit of is covered by Vijayan in the lab class. So I'll be doing system call handling first of all, and I'm taking a special system call, that is Fox system call, as an example just to teach you process creation also. So process creation per se will be starting in the next lecture because it's a difficult concept to understand. So I'll just introduce what are the various difficulties in process creation. But in general, what happens when there is a system call? And now you have enough idea that what is going to happen in system call. So all those things which are there in the interrupt handling would be performed. We have already covered this. And then you can go to trap frame and you can get the trap number, that is system call. And then from there, the system call execution will start. XV6 supports several system calls given in sheet number 35 to 36. I'll be uploading the XV6 code today, which we are using in this class, and that will be available in your class material. System calls are also handled by trap function. The system calls that user programs in XV6 can use are defined in file user.h. It's a header file of your C library. User space C library of XV6, user.h file is there. And now the code in uses.s, this is a system library, converts the user library function calls to system calls, and to convert into system call, you need to invoke the int instruction, because int instruction is needed to shift the control from user mode to kernel mode. The system calls are also going to be handled as interrupts, albeit a software interrupt. And you know that for all system call, there is only one argument, that is 64. So as soon as this int instruction is invoked by uses.s, while you are converting a library function call to actual system call, then uses.s will supply the argument number to this, that is 64, which is common for all system call, with a suitable argument indicating that the trap is due to a system call. Main trap handling function looks at the argument as I have shown you, line number 3350. As you can see here, if trap number is equal to t underscore system call, then this particular function will be called syscall, which will handle the particular system call. Let's see here. Main trap function handling function looks at the argument passed to int, realizes that this trap is a function call, calls the common system call processing function syscall in the kernel. While you were converting user.h C library function of system call to actual system call by uses.s, at that point of time, you will store the actual system call number to this EAX register. In uses.s, system call number is pushed into EAX register. Now this common syscall function looks at this syscall number and invokes the specific function corresponding to that system call. तो एक स्टेप और ज्यादा है इसमें. जब पता चल गया ये सिस्टम कॉल है तो एक sys कॉल फंक्शन दूसरा सी फंक्शन कॉल हुआ. कौन सी सिस्टम कॉल हैंडल होनी है, फॉक है कि एग्जिट है कि एग्जिक है, whatever is going to be known by the system call number which was pushed by uses.s into EAX register. Fine. So let's see the syscall function 3624. You can see here ट्रैप फ्रेम में के EAX रजिस्टर को अपन देख रहे हैं, क्योंकि EAX में हमने क्या किया है, यूसेस ने सिस्टम कॉल का नंबर डाल के रखा हुआ है. ये सिस कॉल फंक्शन है जो कहां कॉल हुआ था, ट्रैप फंक्शन में. ट्रैप फंक्शन किसने कॉल किया था, ऑल ट्रैप फंक्शन ने. ऑल ट्रैप फंक्शन ने क्या किया था, स्टैक में सब वैल्यूज को स्टोर किया था इन कोलैबोरेशन विद इंट फंक्शन. इंट ने बाकी चीजों को स्टोर किया था. एंड नाउ दिस syscall function will go and fetch the number from EAX register, and depending upon this number different system calls, fork, exit, wait, kill, get PID, SBRK and sleep, and all these function system calls will be handled. So there is no much difference between interrupt handling and system call handling. System call handling are a special case of interrupt handling. A common number 64 is assigned as an interrupt number. You go to trap function, then you call syscall function. In syscall function you go and fetch the value in EAX. EAX में क्या है, system call का argument है. argument कहां से मिला, जब यूसेस ने कन्वर्ट किया user.h लाइब्रेरी को सिस्टम कॉल में. फाइन. It pushes the system call number into EAX register, and later on in syscall function this EAX register is fetched and accordingly system call is handled. So we'll stop here. If there are any questions you can ask. Your lab assignment of week 3 is uploaded. And now I think, Brajen, I think now there is no problem in doing that lab assignment. I have covered everything.
Yes, sir. Yes, sir. Yes, sir.
I think I have covered everything in detail.
Yes, sir.
Any questions from anybody? Okay. If there are no questions, then thank you.
Sir?
Yes, yes.
Sir, in the EAX, when system call is done, the common argument is 64.
No.
Yes, sir. That was the question.
No. फिर से सुनो. int में int इंस्ट्रक्शन किसने कॉल किया, ध्यान से सुनो. uses.s ने. क्यों कॉल करना पड़ा, फिर से सुनो. जब अपन सी में इनपुट आउटपुट हैंडलिंग कर रहे थे फाइल पॉइंटर यूज करके, तब एफ ओपन यूज करते थे तुम ना?
यस सर, यस सर।
अब एफ ओपन तो सी फंक्शन है लाइब्रेरी का,
हाँ सर।
वो stdio.h में डिफाइंड है।
हाँ यस सर।
अब वो फाइल जो एफ ओपन फंक्शन है लेटर ऑन यू यूज करेगी ओपन सिस्टम कॉल।
हाँ यस सर।
ठीक है, तभी हम फाइल ओपन कर पाएंगे।
यस सर।
वही कुछ यहाँ भी है कि यहाँ user.h लाइब्रेरी एक दी हुई है,
यस सर।
यहां से आप यूजर स्पेस में सिस्टम कॉल करोगे।
हाँ सर।
वो जो कॉल फंक्शन करोगे आप सिस्टम कॉल का, उसको यूसेस कन्वर्ट करेगा
हाँ सर।
सिस्टम कॉल में, एक्चुअल सिस्टम कॉल में।
यस सर।
और जब कन्वर्ट करेगा तो इंट इंस्ट्रक्शन इन्वोक करेगा, क्योंकि उसको सेव करना है सब कुछ। तो वो यही सीपीयू वाला इंस्ट्रक्शन बोलेगा, भाई इसको चलाओ, क्योंकि और कोई कोड अभी हम चला नहीं सकते, हमको ऑल्टर एफ को कॉल करना है। ठीक, और जब वो इंट कॉल करेगा तब इंट का आर्गुमेंट 64 देगा। इंट का आर्गुमेंट 64 देगा। अब इंट जब चलेगा ट्रैप फ्रेम बन जाएगा। ठीक है, ट्रैप फ्रेम में ट्रैप नंबर क्या जाएगा? 64 जाएगा। और जब हम ट्रैप फंक्शन चलाएंगे, ट्रैप कहाँ डिफाइन था? 1 मिनट। तो हमको पता चलेगा ट्रैप नंबर, और वो पता चलेगा ये सिस्टम कॉल का है। मैं फिर से बता रहा हूँ, ट्रैप फ्रेम तक समझ में आया ना कि 64 चला गया?
हाँ सर।
1 मिनट। इंट में 64 तुमने डाल दिया, ठीक है, जिसको T_ सिस्टम कॉल भी कहते हैं, सिस कॉल भी कहते हैं। मैक्रो ट्रैप कहाँ है? लाइन 3350 पे। See here. So we'll see the trap number, और यहाँ पे 64 हमको मिलेगा T_ कॉल। ओके, ये 64 जब मिल गया तो ये इफ इंस्ट्रक्शन एग्जीक्यूट होगा। ठीक, फिर अपन क्या कॉल करेंगे? सिस कॉल। और सिस कॉल में क्या किया अभी हमने EX रजिस्टर को पढ़ा। उस EX सिस्टम कॉल का नंबर है कि फॉक है कि वेट है कि एग्जिट है। ठीक है,
वो यूनिकली आइडेंटिफाइड
है। तभी तो तुम जब लैब में अपना नंबर जोड़ रहे थे ना, अपना नया सिस्टम कॉल के लिए एक नंबर जोड़ रहे थे ना। 1 मिनट, एक कॉल लेनी पड़ेगी। You got it now, Abhinav? Huh? Okay. Any other question? If there are no question, then thank you.
Okay, sir. Thank you.
Okay, then thank you.